So this is a discussion of the material in section 2.5. So in 2.4, we talked about limits going to a finite number that would make the denominator essentially be zero. So the limit would then either go to infinity or negative infinity. You approach a vertical asymptote. So like 1 over x, the hyperbola, as we approach x from the right, it goes to positive infinity. And as we approach x from the left, it goes to negative infinity. This doesn't seem to be very cooperative. Yeah, okay, yeah. So like here it'd be 1 over x. Yeah, so as you approach x from the right, yeah, it goes to a positive infinity, and we approach x equals 0 from the left, it goes to negative infinity. So that's what we talked about in section 2.4. And now we're going to talk about what happens is instead of x going to some finite number, like here it's going to x equals 0. What happens when x goes to infinity or x goes to negative infinity? And we're going to see that in some cases it actually approaches what's called instead of a vertical asymptote, it approaches a horizontal asymptote. So there we have just an example there, the function of 4x plus 3 in the numerator and 2x minus 6 in the denominator. Yeah, you can just take some order pairs. Yeah, we're going to learn kind of, algebraically how to see that the graph eventually approaches y equals 2. Eventually, 4x plus 3 for very, very large x, 4x plus 3 behaves like 4x, and 2x minus 6 in the denominator behaves like 2x. Like for when x is a million, adding 3 doesn't really mean a lot, and subtracting, when x is a million, subtracting 6 in the denominator doesn't really mean a lot. It's like you have $1 million, one more dollar, probably doesn't mean a lot. Okay, so I always kind of think of it that way. Okay, so you don't have to know definitions, but you should kind of have an idea of when you just visually, what do we mean when we talk about a horizontal asymptote? So it's saying that as x goes to infinity, the graph of f of x approaches a horizontal line y equals L, either as x goes to infinity or x goes to negative infinity. So yeah, so there where you see it circled in that yellow. Yeah, so if c is not a positive constant, if c is a constant, the limit of c over x to the r goes to 0 because the denominator gets huge. For x, as x goes to infinity, 1 over x becomes very, very small. Like 1 over a million is small, and then 1 over a million to some, like let's say r is 2, 1 over a million squared is even smaller. Yeah, so if the denominator is fixed, a finite number, and the denominator goes to infinity, yeah, it's going to 0. So there we see examples like example 2a, like 4 over x plus 3. Yeah, the denominator becomes huge for large x. So 4 over infinity will become 0. And b, yeah, again, so in that case, well, the limit as x goes to infinity, well, 6 doesn't go anywhere, right? If you just look at the plot of y equals 6, it never changes. But 3 over x goes to 0, and 5 over x cubed goes to 0. So yeah, I'm talking about right here. Yeah, so that limit would go to 6 plus 0 minus 0. Okay, so here, let's just look at a few more example here. So not the limit, like, and we saw that last example, the limit doesn't necessarily go to infinity, right? When you have 3 over x goes to 0 as x goes to infinity. 5 over x cubed goes to 0 as x goes to infinity, but 6 does stay 6. So the limit isn't necessarily 0 here. Okay, so let's just talk about what's called indeterminate form, which you talk about more in calculus. And you get these limits of infinity over infinity, and those are the ones that maybe cause us not grief, but it's not obvious what the answer is. Like a constant over infinity, we know is 0, but yet infinity over infinity. So the question is the numerator going to infinity faster than the denominator is going to infinity? Are they going at the same rate? Or is the denominator going to infinity at a much faster rate than the numerator? And so look at 4a. So as x goes, this is what I said before, as x goes to infinity, 4x minus 1 is essentially 4x. I mean, let x be a trillion. 4 trillion minus 1 is almost the same as 4 trillion. And the same thing in the denominator. A trillion plus 3 is about a trillion. So it's only, so we're talking about super large x. all we care about are the highest order terms, the term with the highest degree, like in that case, the highest term is x to the first. But if you see up there, I also did it, and you probably learned this somewhere in your algebra courses. I did it algebraically. So we're going to divide the numerator and denominator by x. So we get, yeah, 4, right here, we get 4 divided by 1 over x, and we get 1 plus 3 over x. And now as x goes to infinity, yeah, you see 1 over x goes to 0, and 3 over x goes to 0, and it turns out just to be 4. So really what you can do is just take the coefficient of the highest order terms. So like in B, what's the coefficient of the highest order terms? Well, the highest order term here is, well, there's -1, and then there's 1. And so it goes to -1 over 1 because x squared grows much faster. And again, like if x is a trillion, you square it. Well, a trillion squared is really, I'm not sure what trillion squared is. Well, I think trillion is 10 to the 12th. So you square it, you get 10 to the 24th. So x squared, and I'm talking about for large x. If you're talking about like 100, this doesn't work. I'm talking about like you're getting x is a trillion, x is, a trillion times a trillion. X squared becomes much bigger than x. So the function behaves for very, when you're way out near the endpoints, the numerator behaves like minus x squared. I'm talking about b there. And the denominator behaves like x squared. But again, when you're taking these limits and you get infinity over infinity, if the degree of the numerator and the denominator are the same, you can just look at the coefficients. Okay, so now what we'll see is a little bit different here. Okay, so in A and B, I just want to make clear, I say you can just look at the coefficient. That only works if the degree of the numerator and the denominator is the same. And I should have mentioned that before. So like in A, the highest degree is 1, like 4 to the x to the first, and in the denominator, it's x to the first plus 3. So the highest degree is 1. In B, the highest degree we see is x squared. The highest degree is 2. So it's the same in the numerator and the denominator. Okay, but C, it's a little bit different. Do you see how the C here? So here, the degree of the numerator is 2, and the degree of the denominator is 1. So in this case, the numerator grows much faster. They're both going to infinity, but the numerator just gets there fast. I mean, how do you actually get to infinity? So maybe we should have like a special office hour on that. But anyway, yeah, and again, you can just do the algebra, but basically, do it like I did up there, right here. You can just divide the numerator and denominator by x, and you'll get the same answer. But for very, very large x, the numerator behaves like x squared. The 5x doesn't matter for when x is like a trillion or a trillion times a trillion, and the denominator behaves like 3x when for very, very, very large x. And so you get x cubed, you get x squared over 3x. So that's x over 3. Yeah, it goes to infinity, and that's because x squared, see, you can just look at it. You can see the numerator is, the highest degree is x squared. The denominator, the highest degree is x. So you got that 3x. And so that polynomial in the numerator grows much faster than the polynomial in the denominator. Even though they're both going to infinity, the numerator just grows a lot faster. So the limit is infinity for C. So A and B, it's a constant. For C, it's infinity. Oh, and D is one of our favorite limits for this section. Okay. So, it's the exact opposite of C. The degree in the numerator is 1. The degree in the denominator is 2. They're both going to the numerator and the denominator. If you actually graph 4x minus 3, it's just a straight line that just goes up and up and up. The denominator, the graph is a parabola. This goes up and up and up. And if you actually graph the two in the same plot, that parabola would eventually go up much faster for large x. Okay, but again, the numerator behaves like 4x for large x. The denominator behaves like x squared for large x. So you get 4x over x squared. And so you get 4 over x. And now the limit goes to 0. Okay, so in the numerator and the denominator grow at the same rate. You just take the coefficients of the highest order terms. When the numerator grows much faster than the denominator, they're both going to infinity, but the numerator grows much faster, the limit's infinity. And when so when the degree is higher, right, the limit is infinity. And so then in D, where the denominator grows faster than the numerator, in other words, the denominator has the highest degree, a higher degree, the limit goes to 0. And then we kind of just write that in English. So let's say you have this P of x and Q of x. So I'm looking at this square right here. They both go to infinity. But if the degree of P of x is less than the degree of Q of x, yeah, we saw in that last one, D, the limit goes to 0. The degree of P of x is greater than Q of x. Well, you saw there in C, the limit goes to infinity. And then for A and B, we just saw that the degree went to, that the limit went to a constant when the degree of P is equal to the degree of Q of x. It goes to a constant. So here's just a few more of these. And so now let's just find the horizontal asymptote. So you look at the limit as x goes to the left and to the right. So x goes to infinity to the left and x goes to minus. And let me say that one more time. We're looking at A. What are the horizontal asymptotes? Let's first consider the limit as x goes to infinity. And once again, the numerator grows like 3x for large x, and it grows like minus 2x for large x. And so it just turns out as x goes to infinity, the limit is 3/2. Okay, so the graph would approach the line y equals minus 3/2. And then that same thing for x goes to negative infinity. It turns out to be the same quotient. So it doesn't, because you see that again, the numerator behaves like 3x and the denominator behaves like minus 2x. So, or it behaves like for very large x in absolute value. It doesn't matter which way you go. The quotient 3x minus 5, 4x minus 2 behaves like 3x over minus 2x, or just minus 3/2. So the horizontal asymptote is y equals minus 3/2. This HA, I should have said before, that means horizontal asymptote. It's like VA means vertical asymptote. So 3B is maybe a little bit harder. Okay, not that much harder, but we see the degree is 1 because of the square root of 4x. So there, for positive, we're writing x to positive infinity, it behaves like, we just throw away the lower order terms. So 3x in the numerator, square root of 4x squared in the denominator. But x is actually positive, so there you see absolute value of 2x. But since x is positive, it behaves like 3x over 2x, because the absolute value of 2x is the same as 2x, where x is positive. So it goes to 3/2. Okay, here, so now, so what happens here? So x is going to go to negative infinity. Okay, so the denominator, so again, once again, it behaves like 3x over 2x, but now the x is actually going to be negative, so it goes to minus 3/2. So yeah, so if you actually graph this function right here, as x goes to positive infinity, the graph would approach the line y equals 3/2. As x goes to negative infinity, it would approach the line y equal minus 3/2. And so students, let's look at C here. And I really encourage you to graph these. I did graph C here. Right? And actually I put it at the bottom of the page here. So now we're going to look at, yes, C. Let's see right here. We're going to look at this one right here. And so again, the numerator, they grow at the same degree, the highest order term is x squared in the numerator and the denominator. So we know that so as x goes to positive infinity, or even negative infinity, what happens is that the limit goes to 2. And so there, yeah, so a function can cross its horizontal asymptote. Wow. That's what I was thinking. Okay, so anyway, but here's the graph. I had to put the graph down here. And so here's so here's the plot of 2x squared minus 3x plus 5 over x squared plus 1. And so there you see this, here's this line, y equal 2. So initially, so for small x near, 1 or something, yeah, the graph dips down. But what happens is, of course, I'm only graphing to x equal to 2.5. But for much larger x, it's going to start going back up again and start approaching the line y equal to 2. Yeah, but yeah, so for small x, the graph will, first of all, for x is 0, it's, the f of 0 is 5, and then it kind of dips down. So like when you get close to x equal 2, it's almost 0, and then it starts going back up again to the line y equal to 2. Again, because this is just for large x. For large x, this is 2x squared. This is only true for large x. It's 2x squared over 2, or, oh, that wasn't good. Okay. I'll put that back later. Okay, so anyway, okay, sometimes you see, you're going to have a lot of problems throughout, I think, Calc 1 and 2 with trig. We definitely need to know our trig, or at least know what the graph of the functions look like. So what about the limit of cosine of x as x goes to infinity? Well, here dne does not exist because it goes up and down. It does not approach. Yeah, so it doesn't approach a horizontal asymptote. We know that you just get these cosine waves. Now for sine of x over x, what happens is, well, if x goes to infinity, the sine of x is bounded above and below by 1, but 1 over x goes to 0. And so you can actually prove, yeah, so like here, -1, right here, -1 is less than or equal to sine of x is less than or equal to 1. So if you just divide, whoops, I forgot to put the x in here. Therefore, yeah, 1 over x minus 1 over x is less than or equal to sine of x over x is less than or equal to 1 over x. So yeah, so you can actually use, remember that squeeze theorem, I think, from last time. The limit of 1 over x as x goes to infinity is 0. The limit of minus 1 over x as x goes to infinity is 0. So the limit of sine of x over x has to go to 0. But again, sine of x is just bounded between -1 and 1. And 1 over x, gets smaller and smaller and smaller for large x. So the horizontal, if you actually graph sine of x over x, the horizontal asymptote would be the line y. The graph would approach y equals 0. So here's another one. So remember the last time we learned that the limit, yeah, well, this limit right here, the limit of sine of theta over theta as theta goes to 0 is 1. So what about the limit of sine of 1 over x and the denominator is 1 over x? Well, just let theta equal 1 over x. So as x goes to infinity, theta goes to 0. So and you're going to see this at some point in the course, and I can't remember if it's mostly Calc 1 or Calc 2. But we do these substitutions where we're taking the limit. Oh God, this is a hard limit to take. The sine of x, sine of 1 over x divided by 1 over x. But yeah, you make this substitution, theta equal 1 over x, and as x goes to infinity, theta goes to 0. So this problem, the limit as x goes to infinity of sine of 1 over x divided by 1 over x is equivalent to the problem, the limit as theta goes to 0 of sine of theta over theta, and you get 1. And so making these substitutions is pretty common in calculus. And then and then you can actually do some here's just an application. You have a cost function, and the unit, basically what it's saying is the unit cost of producing X units. So is given, let's say it's given by that function. So it's saying the unit cost is 0.5 plus 5,000 over X. So the more units you produce, the unit cost goes down, right? Because you're dividing by X. You're dividing by the number of units. So yeah, you can see, so if it's 100 units, it's a unit cost of $50.50. 1,000 units, it's a unit cost of $5.50. But if X gets really, like if you make like a trillion, if you make a trillion of these items, your unit cost is only 50 cents. So I think, yeah, that's something we should do this weekend. Okay, so I'm going to stop sharing this. I'll stop the